Good morning, everyone. Welcome to Learning with Vodafone webinar series. Our today's topic for this webinar is scheduling algorithms. In the previous webinar, we have learned about inter-process communication using shared memory and semaphores. Shared memory is a method of inter-process communication where memories that can be simultaneously accessed by multiple programs with an intent to provide communication among them or avoid redundant copies. Semaphore is a variable or abstract data type which is used to solve critical section problems and to achieve process synchronization in the multi-processing environment. Semaphores which allow an arbitrary resource count are called as counting semaphore, whereas semaphores which are restricted to the values 0 and 1 are called binary semaphores and are used to implement locks. Today we are going to learn about two popular scheduling algorithms such as round-robin scheduling and priority-based scheduling, and we will try to calculate average wait time and average turnaround time using these algorithms. Round-robin scheduling is predominantly used in the general-purpose operating systems, where all the processes need to be serviced for a given time quantum so that none of the processes feel that they are starving for a resource. Whereas in case of priority-based scheduling, a particular process which is of a higher priority is always given precedence over the other processes so that the important task is completed on time. This kind of scheduling algorithm is preferred in real-time operating systems. Every application would be comprised of one or more processes which are created with the help of fork system calls. When multiple processes are available, they may need to interact with each other via shared memory and semaphores. But until and unless these processes are not organized properly, that is, which process would come when and for what duration, they may cross each other's path, which may end to deadlock situation. To avoid such situations, we need to understand about scheduling algorithms and their implementation process. Why exactly do we need scheduling? A typical process involves both input-output and CPU time. In a uniprocessing systems like MS-DOS, time spent waiting for input-output is wasted and CPU is free during this time. In multi-programming system, one process can use CPU while another process at the same time can be waiting for input-output. This is possible only with process scheduling. There are different types of scheduling algorithms available, out of which few scheduling algorithms we have mentioned here. The first is first come first serve, where the various processes would be organized based upon their arrival time. Whichever processes would appear first in the queue would also get a service from the processor. Another type is shortest job first, where the process with the shortest burst time are scheduled first. So in that case, those processes which are quick to complete their execution would be entertained first by the processor and processed. Another type of scheduling algorithm is shortest remaining time first. So this is a preemptive mode of shortest job first algorithm in which jobs are scheduled according to the shortest remaining time. Round robin scheduling. In this algorithm, each process is assigned a fixed time in a cyclic manner. Priority based scheduling, which is non-preemptive in nature. So let me clarify here that all non-preemptive scheduling algorithms are those in which the process can not be interrupted from its functioning. If it is a preemptive based algorithm, then the processor have all the rights to request the process to release all the resources it have acquired. It is something like processor can preempt the process and get all the resources immediately when and as required. Whereas in case of non-preemptive algorithms, OS do not have any right to stop the execution of any process. Now, if the priorities of the two processes match, then they schedule according to their arrival time in the priority-based scheduling algorithms. And the next one is highest response ratio next. So in this scheduling, process with the highest response ratio is scheduled. To get this response ratio, we have a formula which says that waiting time plus burst time divided by waiting time. So this will generate me a response ratio. On base of that, we understand that whichever process is of a higher response ratio would be entertained first. There are many other scheduling algorithms available. Here we have just listed few of them. Many more can be read from the relevant resources. You can download the reference material for this webinar from the given link. To complete this webinar, your computer laptop must have Ubuntu 16.04 LTS installed. In case you are using Windows-based laptop, then you should have a VMware workstation or a VirtualBox installed in your system, which is running Ubuntu 16.04 LTS. Now let's understand the implementation of a particular priority-based scheduling algorithm and try to calculate the average waiting time and where the turnaround time in this particular case. So here I have used a Gantt chart to make you understand that how priority-based scheduling works actually. So here we have four processes P1, P2, P3, P4. Each of these processes have been assigned their priorities where the lowest priority number is of a higher priority and the highest priority number is of a lower priority. It means that P3 will get the highest priority among all the processes, whereas P4 will get the lowest priority among all of them. And this is the burst time. So burst time is trying to tell you that for how long a particular process is functional. So this particular example tries to tell me that out of all these four processes, the very first process which is going to get executed is P3 because of its highest priority. The first P3 is going to be functional and that will be functional for burst time of 14. So for 14 burst time, P3 will be active. The next highest priority is P2, who's going to active for 2 burst cycles. So now after P3, P2 comes into the scheduling queue and it is going to be executed for 2 burst cycles. So after 14 becomes 16. Then the next highest priority is P1 and its burst time is 6. So after 16, the burst time is added, which makes it 22. And then finally P4 comes into the scheduling process. And for this P4, the burst time is 6. So 22 plus 6 gives you 28. So this particular thing is a Gantt chart which helps us understand that in what manner what processes are going to be aligned one after another and for what would be their burst time and turnaround time. Now implement this understanding that we have acquired from the Gantt chart using C program on the next slide. So here we have our regular hash include stdio.h. Then we have main function. In main function we have certain arrays in which various elements like process, burst time, waiting time, turnaround time, all of those would be stored. Here we are asking for an input from the user that enter total number of processes we want to work in this particular algorithm. The result will be stored in n. Then it's going to ask enter burst time and priority. With the help of this for loop, the burst time and the priority of the process is being taken as an input from the user and printed on the screen. So at the end of this particular section of the code, the user will specify that with how many processes this priority-based scheduling algorithm is going to be implemented and what are the burst times and priorities for each of the processes assigned. Now here we are trying to implement a selection sort, help us to sort processes on basis of their burst time priority in the ascending order. In this for loop, for the very first iteration, when the value of I goes 0, and then this 0 is assigned to the variable POS, and here we are checking for the inner loop of j that goes to I plus 1. So the very first iteration, the value of I is 0, so the j goes from 0 is assigned to POS and the value of j will be 1. So it starts from 1, it goes to n. So n is like the total number of processes we have. Here it's going to identify that if PR of 1 is less than PR of 0, it means that if the second element is less than the first element, if it is so, then we interchange the positions. So in case it is true, then the positions like the second position is assigned to the first position, and then here swapping takes place between the first element and the second element, between the burst time of first and second element, and in the priorities of first and second element. If it is not so, if your second element is no smaller than the first element, in that case also the swapping happens, but actually it doesn't make any difference because all the elements remain at the same place. So with the help of the selection sort, we are able to organize processes. So in this section of code, we are going to calculate the waiting time for each of the process. Notice when the value of I is 1 and I is less than n, which is a At this moment, the value of n is 4. So considering we have 4 processes for this particular scheduling implementation, the waiting time for the first process is 0. Then for j equals to 0, j is less than I. So at this moment, I value is 1. So j is less than 1. So only one iteration of j will happen. So bt of j, burst time of 0, is equal to waiting time of 1. Here we have already said the waiting time for the first process is 0. The burst time of 0 is what we will include. So the waiting time for the very first iteration will be the burst time of the first process. And that helps us to identify the total waiting time in this particular variable. So if you notice on the Gantt chart, the waiting time for the P3 is 0, whereas the waiting time for the P2 is the burst time of P3. Similarly, the waiting time of P1 is the burst time of P3 plus P2, and the waiting time of P4 is the burst time of P3 plus P2 plus P1. So that is what we are going to implement here. With the first iteration, the waiting time is equal to burst time, that is stored in waiting time of 1. The next iteration, the value of I becomes 2. So at that time, the waiting time for the 2 will be 0, but it will be added with the burst time of the previous processes. Now once we have done this, we got the total waiting time stored in this variable, and we can calculate the average waiting time by dividing the total waiting time with the number of processes available and storing the result in this variable. Now we can print that output one by one, but before we print, we need to calculate the turnaround time as well. So the turnaround time is nothing but the burst time and the waiting time of each of the processes. So we add all of them and we store that in variable TAT. Then we finally calculate the total turnaround time so that we can get average total turnaround time output, where we divide the total turnaround time with the number of processes available, and finally we can print the average waiting time and average turnaround time with the help of these variables on our display. This is a screenshot of the possible output that we will acquire. First we will compile the program, and then it is asking for the enter total number of processes. We can enter total number of processes as 4. Then we have enter burst time and priority. For each of the processes, we have given their burst time and priorities. Based upon that, it have organized all the processes. So you can see that the process 3, which is of a higher priority, P1, come first, and then process P2 of the second highest priority, then process P1 of the third highest priority, and finally process P4 of the fourth highest priority, is dependent upon the burst time of those processes. So finally, here we can get the average waiting time and the average turnaround time. Let me implement this algorithm for you on my Ubuntu console. So to implement this priority-based scheduling algorithm, we compile the program cc space -o priority, and the program name is priority underscore schedule.c. And after compiling, once we execute our binary file, priority, so number of processes, let's say 4. Burst time for the first process is 6 and the priority is 3. Burst time for the second process is 2 and the priority may be 2. For the third process, the burst time is 14, the priority is 1. And for the fourth process, the burst time is 6 and the priority is 4. Once we have given all the inputs, you can notice that all the processes are organized based upon their priorities, and it calculates the average waiting time and average turnaround time for each of the process and mentions it here. I hope you have understood the implementation of priority-based scheduling. Let's move on to our next scheduling algorithm, that is round-robin scheduling.
So let's try and understand the demonstration of the round-robin scheduling algorithm with the help of the Gantt chart, which help us to calculate the average waiting time and average turnaround time. So here we have 4 processes, P1, P2, P3, P4, with their respective arrival times and their burst time. So in this particular example, we have assumed that time quantum is of 2. So here we can notice that P1, which have a burst time of 9, which have arrived at 0. So P1 begins at 0 but it could not complete its entire bus duration of 9, but it will last for only 2 time quantum, and then it switches to the next process, that is P2, which have a burst of 5. So again it will get a share of 2 time quantum. Then it will switch to P3, which have a burst of 3. It will get a share of 2 time quantum, and then P4 for 2 time quantum. Now in the next iteration again P1 comes here, and this time it is like 2 time quantum of P1 added with 2 time quantum of P2. So it makes 4, whereas the bus time is 9, so it can further continue. Similarly, for P2 it is 2 here and 2 here, it makes 4. Bus time is 5, so it can have one more time quantum left. Then for P3 the burst is 3, so here I get P3 for 2 time quantum, but this time the P3 will be for only 1 time quantum, so in total it makes 3. So there's no more bursts left for the P3, so it will discontinue from here. Then comes P4. So P4 have taken 2 time quantums in the previous iteration, and again here P4 takes 2 more time quantum, which completes its 4 bus cycles, so it will also exit. Now in the next iteration P1 will be there with 2, so it makes total 2 plus 2 plus 2, that is 6 time quantums for P1, whereas the burst is of 9, so it will further continue. Whereas P2 would be having 2 time quantum, 2 plus 2 and plus 1, because the burst for P2 was 5. So the moment it gets over, P2 exits, and then P3 and P4 were already exited prior. So the remaining process is P1, which have already taken 6 time quantums. It will take 2 more time quantum to make it 8 and 1 extra to make it 9. So that's how the Gantt chart is organized. Like, hope you have understood the organization of the processes over Gantt chart. Now, if you look to the turnaround time, that how can we calculate turnaround time and waiting time using Gantt chart itself? So, in this particular arrangement, if you see here, that process P3 have a turnaround of 11. So, if you could notice here that this is the last time quantum in which process P3 was available. First, it was available here, and then it was available here. So process P3 have completed its entire span when the value of time quantum was 13. If you notice that process P3 have arrived at 2 time quantum. So what we say is 13 minus 2, which gives me 11. That is the turnaround time for process P3. Now to calculate the waiting time for process P3, if you notice that process P3 have arrived at time quantum 2. So for process P3, the first wait is of only 2 time quantum, and then it will wait because process P3 is coming back at this place. So it will wait for 2 here, 2 here, and 2 here. So the total it is like 2 plus 2 plus 2 plus 2, which makes it 8. So that's how process P3 have got waiting time of 8. Well, let's follow the same example for process P4. The last time quantum in which process P4 is visible is here. So process P4 have completed its span when the time quantum value is 15, whereas process P4 have arrival time of 3. So it makes the turnaround time as 15 minus 3 gives you 12. That's how process P4 have got turnaround time of 12. Similarly, on the other note, for waiting time for process P4 would be like, since the arrival time of process P4 is 3 and P4 happened at 6 time quantum, so basically process P4 have waited for only 3 time quantums in the beginning, and then again it comes here 3, then plus 2, plus 2, plus 1. It would be like 3 plus 2 5 plus 2 7 and 1 8. And after this there was no further P4 samples, so we can have the waiting time for process P4 as 8. I hope you are understanding that how waiting time and turnaround time can be calculated with the help of a Gantt chart. Let's take one more example of process P2. Turnaround time for process P2 would be, so this is the last sample in which process P2 happened and completed is functioning. So at that time, the span of the process P2 was still 18 time quantum, whereas process P2 happened with the arrival time of 1. So it will be like 18 minus 1 gives you 17 turnaround time. Now if we look to the waiting time for process P2, it would be, because the arrival time is 1. Now when we try to calculate the waiting time for the process P2, here we can notice that the arrival time of process P2 is 1. So it means process P2 have started from time quantum 1. So 1 plus 2 plus 2 plus 2. That makes it 7. And then process P2 happened. And then 1 plus 2 plus 2, which makes it 7 plus 1, 8. and 8 and 4, 12. So waiting time of process P2 would be 12. So I hope by now you have understood how to calculate the turnaround time and waiting time with the help of a Gantt chart. So I'm leaving process P1 as an assignment for you. Now when we look into the programming side of round robin scheduling, here we first include the library and then we initialize certain variables. Here we ask for the total process as an input from the user and we store that value in the variable named n. We are creating a for loop with the count variable, and with this for loop we are trying to take arrival time and burst time from the user for each of the processes, and we store them in AT and BT variable. We have also stored a copy of the BT array into the RT array. Here AT stands for arrival time and BT stands for burst time. In this section we are asking for the time quantum, and that time quantum will be stored in the variable time underscore quantum. Now here we have a for loop. In this for loop, we are trying to understand that if the burst time is less than the time quantum, then burst time gets stored in the time variable. Whereas if the burst time is greater than the time quantum, then total burst time is calculated and stored in time. Those situations where the process have a burst time which is higher than, let's say, in this particular case, our time quantum is 2. If we have a process whose burst time is less than 2, then that will be processed in this section of a program, whereas for all other processes with the burst time of more than 2 will be processed in this section, and the total time is calculated and stored in the variable time. Here, if there's no more burst time left, so all the burst times have been exhausted in their respective time quantums. So we'll calculate the waiting time and turnaround time with the help of this formula. The turnaround time is equal to the total process execution time minus process arrival time. The turnaround time is equal to the total process execution time minus process arrival time. Whereas the waiting time is calculated by total process execution time minus process arrival time and minus burst time. With the help of this formula, we have calculated the total waiting time and total turnaround time of each of the processes. Now to get the average waiting time, we divide that total waiting time by n, where n is the number of the processes which we are going to use in the scheduling algorithm. Similarly, to calculate the average wait turnaround time, we'll use the total turnaround time divided by the total number of processes, which is 4. So with this, we have tried to figure out the average waiting time and average turnaround time for given processes with the help of round robin scheduling. Here's the output. Here's the output. First we compile the program, and when we execute, it asks for the total number of processes that you want to work with. So we have given 4, and this is the arrival time of each of the process and the burst time. So for the process 1, the arrival time is 0 and the burst time is 9. Similarly, for process 2, arrival time is 1 and burst time is 5. For process 3, arrival time is 2, burst time is 3. And for process 4, the arrival time is 3 and burst time is 4. We have also given the time quantum of 2. After performing the computation, the result for each of the processes have been stored here. It also produces average waiting time and average turnaround time as displayed in the output. Let me demonstrate you this execution on my Ubuntu console. First, we will try to compile the program using GCC compiler -o, name of my binary file, and the name of my C program. And once we execute the program, it will be like it's asking for the inputs. The total number of processes that we are going to work with is 4. Process 1, the arrival time is 0 and the burst time is 9. For process 2, the arrival time is 1 and the burst time is 5. Process 3, the arrival time is 2 and the burst time is 3. Similarly, for process 4, the arrival time is 3 and burst time is 4. Now it's asking for the time quantum. If I give the time quantum of 2, so this is the output that we are expecting as shown. Now let's move back to our webinar and continue our discussion. So I hope by now you have understood the implementation of round robin scheduling algorithm using C programming. Now as per the summary of this webinar, in this webinar we have learned about two popular scheduling algorithms, priority based and round robin scheduling. Round robin scheduling algorithms are typically used in general purpose operating systems, whereas priority based scheduling algorithms are primarily used in real time operating systems. In our laptop, mobile devices, round robin scheduling algorithms are used so that all the applications get service from the CPU and multitasking could be witnessed. In mission critical areas such as nuclear power plants, healthcare, aerospace, etc., multitasking is sacrificed to meet deadlines of certain applications to get the best results in the given time frame. Students can implement other popular scheduling algorithms and compare the result to identify the best algorithms in any given scenario. I hope you have enjoyed the webinar. Thank you for watching.